In 4.1, we're going to look at the graph of polynomial functions and look at some properties with the graphs. Now in calculus, we use polynomials extensively, especially when we need to approximate the value of more complicated functions. The reason why we do this is because polynomial functions are very nice functions to work with. And the reason why they are nice functions to work with is because they're continuous. Nice, smooth, continuous functions. So that means there's like no gaps, no sharp corners. And the domain is negative to positive infinity. So it's a nice, smooth function from x values of negative infinity all the way to positive infinity. We're going to look at the general form of a polynomial, and if you haven't seen the general form, this formula may look a little bit intimidating, but it's just a way to describe a general polynomial. We'll look at a specific example in just a minute. But when we are talking about a general polynomial, it's going to be some p of x. So we typically use p for polynomial. And then we would write the terms of the polynomial from the variable x of highest degree to lowest degree. So we always go highest exponent to lowest exponent. This reads p of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus continues on to a sub 1 times x plus a sub 0. Blah, blah, blah. So what does that mean? Well, each of these a values is a real number. It's just the coefficient on the x. And the condition is that that first one can't be 0. The exponents, these n's, it's a whole number. So a polynomial will not have negative exponents or fraction exponents. It'll always have exponents on the variable x, 0, 1, 2, 3, and so on. Notice that we stop at a sub 1 x to the 1, even though we don't write that. But I will. And then the a sub 0, notice that we don't write x to the 0, but remember x to the 0 is just 1, so we could put the x to the 0. Then you notice that pattern is that the subscript or the index on the a always matches the exponent on the x. So a to the n, x to the n, a to the n minus 1, x to the n minus 1, a to the 1, x to the 1, a to the 0, x to the 0. Let's look at an example of a polynomial. Let's say we have p of x equal to 3x to the third minus 4x squared plus 8. In this particular case, notice that the highest exponent is 3, so we have n is equal to 3. This 3 is going to be our a sub 3 times x sub 3. Negative 4, so we include the sign in front. So the negative 4 would be the a sub 2 to match with the x sub 2. And then notice that there's no a sub 1. That's because a sub 1 in this particular case is 0, so we don't write it. And then the 8 would be an a sub 0. That would be what we call the constant term. So let's look to the right where we have all this vocabulary. When we look at this a sub n, x sub n, that very first term, we call that the leading term. Your book will call it the dominating term, but most books use leading term. And the reason why most use leading term is because when you just look at the coefficient on the x to the n, which would be this a sub n, it's called the leading coefficient. So leading term has a leading coefficient, and the vocabulary is consistent. So I prefer to stay with leading term. Now the next thing we talk about is the degree. So the degree is going to be the largest exponent, which we call n here, on the variable x. So n is going to be your degree. And the last thing we're going to look at is this a sub 0. That's what we call the constant term. Let's look at some graphs of different degrees. So these are just samples of different types of polynomials that we've already talked about a few of these. So notice that lines are polynomials and quadratic functions and cubic functions. These are all polynomials, but they're polynomials of different degrees. So if we have a constant function, which would be degree 0, now remember this horizontal line would be an equation like, oh, I don't know, y equal to, let's pretend like it's passing through 2. So there's no variable x in there, which is why it's called a constant function. So this would take the form of a polynomial p of x equal to 2, which would be the a sub 0. Now when we go to our linear function, that is degree 1. So remember a linear function, we could write it as y equal to mx plus b. So notice the x has exponent 1. The general polynomial form for a linear function would be p, oops, did not want to do that. Why, Storm? Would be p of x equal to a sub 1 x plus a sub 0. So in this particular case, our a sub 1 is the slope. X plus a sub 0 would be that b value. And then when we look at our quadratic function, which is degree 2, that will take the form p of x equal to a sub 2 times x squared plus a sub 1 times x plus a sub 0, and so on. So you get the point. Let's go to example 1, and then we'll go back up to those graphs for just a little bit. In example 1, we want to state the leading term, leading coefficient, degree, and constant term for this polynomial. Well, first of all, we notice that the leading term is the first term, negative x to the 9. In part B, we just want the leading coefficient. So that would be the number on x to the 9, which would be a negative 1. Because remember, this is negative 1 times x to the 9. And then C, degree, that would be 9. That's the largest exponent. And then the constant term would include the negative, the minus, the sign in front stays with. So it'd be a negative 8. Let's go back up to these graphs. And I don't know if you noticed that as the degrees get larger and larger, the graphs get more squiggly, which is not a math term. But basically, let's see, degree 0, we have this horizontal line. Degree 1, we start getting some slant in there. Degree 2, look at what happens in degree 2. We start out with this particular graph as decreasing. So recall that if it goes down, it decreases. And then it's going to stop. It's going to turn and change direction and become increasing. And that's degree 2, it turns once. In degree 3, it starts off for this particular graph as increasing, and then it stops, it turns, and then it starts decreasing, stops, and then turns and increases. In degree 4, we have, for this particular graph, we have decrease, stop, turn and increase, stop, turn and decrease, stop, turn and increase. And then when we look at this last one, we see that we have 1, 2, 3, 4 turns. So let's go back and look at this. Let's see, we'll start with the degree 2. Degree 0, 1, there's no turns. When degree 2 turns once, degree 3 turned twice, degree 4 turned 3 times, 5 turned 4 times. And that brings up us to this little box at the bottom. It says the number of turning points for a polynomial of degree n greater than or equal to 1 is at most n minus 1. So if we look back up at the linear of degree 1, so this is degree n greater than or equal to 1, and that's the one that I didn't look at. So this is degree equal to 1. N minus 1 is going to be 0. So degree 1 has 0 turns. Degree 2 has n minus 1, which would be 1 turn. But it doesn't have to have 1 turn. It's at most. Okay, so that's the important part. At most, n minus 1 turns. It could have less. In example 2, we want to state the maximum number of turning points for the given polynomial. Well, the degree here is 32. So n minus 1 is 31 turns. I'm going to go back a little bit to these functions again. And notice that at that turning point, that's where the graph will either be at a low or at a high. I like to call them peaks and valleys. So if we look at this degree 2, notice that the point here would be the lowest point. It's a valley, and we have this lowest point. So that would be a minimum value, right? So we're talking about the y values. That's when the y is the smallest. If we look at the degree 3, we have these 2 turning points. Now for degree 3, notice that the ends go to positive infinity, and then we have another one going down to negative infinity. So the y values go from negative to positive infinity, which means there's no maximum or minimum y value for this function. But let's just look at these peaks and valleys. So if we look at this first peak, notice that if I just look at values near that peak, I can see that that is a maximum value, but just for values near there. So this would be like a local max value. And then if we look at this little valley down here, that would be like a local minimum value. So I'm just going to put min. So although there is no absolute maximum value or an absolute minimum value, if we look at these peaks and valleys, these turning points, they could be maybe just local minimum values or local maximum values. Again, look at this degree 4. And we look at this local min. And this one is a local min as well. Because near those values, it's the smallest. But these are also absolute minimum values, because there are no y values smaller than those values. So not only is it an absolute minimum value, there are also these little local minimums. And then we have this local maximum value up here. And it's only local because there is no absolute it cannot be the absolute max because of the endpoints. They're just going up and up and up to positive infinity. So the y values are going to continue to grow, but just in that one little small area, that would be locally a maximum value. So that's something that we're going to talk about next. We're going to talk about what we call extrema. So when we talk about extrema, that would be exactly what it sounds like. Extreme values. This would be our minimums and our maximum. So something to note is when we talk about value, we're talking about the y value or the p of x. Now that we understand what absolute and local minimum and maximum values are, we're going to look at the formal mathematical way that we describe it. So if we have these absolute and local extrema, we're going to let c, which is an x value, be in the domain of our polynomial p of x. So if we put c into our polynomial, we'll get back a y value that's p of c. It's going to be an absolute maximum if that y value p of c is greater than or equal to all other y values p of x for all x in the domain of p. So all that's saying is that that y value has to be the largest. If we look at this graph here, we can see that we have an absolute maximum. It looks like maybe 110. It's the y value. It's going to correspond to a c value of 3. So that would be our c value, and that corresponds to an absolute max. Because no other y value is larger. That is the largest y value. If we look at p of c as an absolute minimum, it just says that p of c, that y value, has to be smaller than or equal to all the other y values for x in the domain. And on our graph here, it doesn't look like we have an absolute minimum. And that's because if you look at the ends of these graphs, they just keep going on forever and ever to negative infinity. So it doesn't matter what c value we pick, we can always find a smaller and smaller and smaller y value. So in this case, there is no absolute minimum value. Let's look at the definition for a local maximum and a local minimum. So we have a local maximum if, same thing, the p of c is greater than or equal to the p of x. But instead of all x in the domain, so for all x values, it's just near, x values near that c value. So that's why our local max would be these 2 points. Oh, again, I use that. The absolute max is also a local max. But this other value here that corresponds to, it looks like -4, and the y value looks like it's 40. This is a local max, but it is not an absolute max because there is a y value that is larger. And then when we look at our local minimum, oh, look, I put maximum twice. I got to change that. Somebody was copying and pasting. If we look at our local minimum, it's going to be less than or equal to for x near that point. And then corresponding on our graph, we have this local minimum. And the y value there would be a negative 20, but it's not an absolute minimum because there are smaller y values. Let's look at example 3. For this polynomial f, we're going to give all local extreme points and state whether whether each is a local minimum or local maximum. And then we want to know if there's any absolute minimums or maximums. And in a little while, when we look at example 4, you'll understand why I underline the word points. That just means that we want to write it as an x and a y value. Okay, so local extreme points. Why don't I start with local max? So we're looking at all our peaks. It looks like we have local max, local max. So that would be the point negative 3, 2, and we have another point which would be 2, 1. What about local mins? Looks like there's two valleys or dips. That would be negative 1, negative 3, and 4, comma, negative 1. So we wrote them as points. Now, is there a local, or is there an absolute minimum? And the answer is no, because if you look at the left side of the graph, this goes on forever and ever to negative infinity. And then if we look at the right side, it goes up to positive infinity. So there is no absolute min or max. In example 4, we're supposed to A, state any absolute minimum or maximum values, and B, state any local minimum or maximum values. So values here. And the difference is when you're asked to find a value, you only list the y value. You don't list the point. Part A, absolute minimum or maximum values. Well, the ends go towards positive infinity. So no absolute max. But we do have an absolute min of, okay, so let's go down to the lowest y value, which looks like it corresponds to negative 4. And that's all I list, just the y value, negative 4. Let's see, part B, we're supposed to state any local min or local max. So we have local, locan, local, maybe, min of, and there's actually two of them. So we had the negative 4, that is a local min, but we also have this other local min. Now remember, it's the y value of negative 4, and the y value that corresponds to an x value of 4 is negative 1. So we have local min of negative 4 and negative 1. Do we have any local max? Yes, right here when x is equal to 2, y is equal to 0, so local max of 0. Another important property with polynomial graphs are the end behaviors. And I'm going to go back to the graphs that we had in the beginning. I'm leaving off the first one, degree 0. I'm just going to look at degree 1 and up. So when we talk about the end behaviors, it's really important to not only know where your graph begins, but also where it's going to. Where's it ending at. Even though polynomial functions go on forever, we want to know in what direction it's going to go on forever. Is it going to go to positive infinity, negative infinity, and so on? So when we talk about the end behavior, what we're really saying is, okay, look at what happens to the graph as the x's either go towards negative infinity or positive infinity. So as your x values go towards negative or positive infinity, what's happening to the y values? So the y values would be what's happening to the graph. Where's it going? So if we look at our graphs again, and here, why don't we take a look at the difference between degree 1, degree 3, degree 5, and then we'll go ahead and look at degree 2, degree 4. So if we look at 1, 3, 5, so those are odd numbers, something you should notice is that as the x values go to positive infinity, the y values are going to positive infinity in this particular graph. And as the x values go towards negative infinity, the y values will also go to negative infinity, just for this particular graph. But remember, this is a line. It can always have a negative slope. This particular example showed a line with a positive slope, but we could also draw a degree 1 linear function with a negative slope. So now let's look at what happens as x goes towards positive infinity, the y values go to negative infinity. As x goes towards negative infinity, the y values go up towards positive infinity. So what's important to note is that it doesn't really matter if the x values are going negative to positive infinity. The y values are always opposite. They're either going to go positive infinity, or negative infinity, positive infinity. But the ends are going in the opposite direction. If we look at degree 3, we'll see that it's doing the same thing. Look at the ends here. You have, as x goes towards positive infinity, this graph goes up to positive infinity. As x goes towards negative infinity, the graph is going down to negative infinity. So the behavior is opposite. One side goes to negative infinity, the other side goes to positive infinity. But we could have drawn this a different way. And in that case, it's going to go positive infinity, negative infinity, but it's still opposite. One is positive, one is negative. And look at degree 5, same thing happens. We have positive infinity, where are you? We have a positive infinity, and we have a negative infinity. And if we flip that graph, it would be positive infinity, negative infinity. So that tells us that there's a pattern here. If the degree is odd, 1, 3, 5, then the behavior at the end of the graph is going to be opposite. One end will go to positive infinity and the other end would go to negative infinity. But let's look at the degree 2. If you look at degree 2, notice that the ends in this particular case are both going up to positive infinity. So they're going in the same direction. Now, if this were a parabola opening down, that would mean that both ends are going to negative infinity. So if the degree is even, then the ends are going in the same direction. If the degree is odd, the ends are going in opposite direction. Let's look at degree 4. To degree 4 again. Positive infinity for this particular case. If we flipped it, then they would both be going down to negative infinity. And that brings us to this box here, which is the end behavior of polynomials. So in general, Polynomials, the way they behave at the ends depends on their degree. So if the polynomial has an odd degree, like we see in these first two graphs, oh, I don't want that. There we go. So if it has an odd degree, the end behaviors will behave in either one of these ways. It'll either start with a y value of negative infinity and then end with a y value of positive infinity, or start with a y value positive infinity to negative infinity. And the behavior depends on the leading coefficient. So if you look down at the bottom, if the leading coefficient is positive, so what that means is remember your leading coefficient is that a sub n? No. So if your a sub n is greater than 0, if it's positive, what's going to happen is as the x values get closer and closer and closer to negative infinity, the y values will also get closer and closer to negative infinity. So you see this arrow here, x arrow negative infinity, y arrow negative infinity. When we see that arrow in this particular context, it means x approaches negative infinity, y approaches negative infinity. So this reads y approaches negative infinity as x approaches negative infinity. And here our y will approach positive infinity as the x goes towards positive infinity. Now if the coefficient, the leading coefficient, is negative, then what's going to happen is opposite. If the x value goes to negative infinity, the y value will do the opposite. It will go to positive infinity. And if the x value goes to positive infinity, the y value will go to negative infinity. So again, this is when the leading coefficient is negative, so this would be a sub n less than 0. If we're looking at an even degree, think parabolas, right? The ends either both go up to positive infinity, as in this first example, or they go down to negative infinity. Now they're going to go up to positive infinity if the leading coefficient is positive. So if the leading coefficient, a sub n, is greater than 0, then positive means up. If the leading coefficient is negative, negative means down. Okay. So that would be a sub n less than 0. And that's the 4 choices that you have for the end behaviors of a polynomial. In example 5, we're going to describe the end behavior using one of these diagrams. For part A, we have this polynomial, and what we really want to look at is just the leading coefficient and the degree. Notice in this first polynomial, we have 7, which is odd. So it's an odd degree. And we have 2, which is positive. And I'm just going to put coefficient. So odd, positive. Odd means the ends go in opposite direction, but since the leading coefficient is positive, it's going to go negative to positive. So that would be that first choice in our 4 choices. Part B, we have 6 is the degree, so it's even. Negative 4 is the leading coefficient, so that would be negative. So even would be one of these last 2 choices, but since it's negative, it's going to go down. And then in part C, we have 3 is odd degree, negative leading coefficient. So that would be this diagram from positive infinity, and then the other end goes to negative infinity. Part D is even degree and positive leading coefficient. So even positive would be up, both ends up. The last thing we're going to talk about here are x-intercepts. So recall when we're looking at linear functions, when we talked about the x-intercepts, those were our zeros. But then we were talking about complex numbers. So now we want to make the distinction that these zeros are real zeros. So the x-intercepts are where we have real numbered zeros. And it turns out that the number of x-intercepts for a polynomial of degree n will have at most n x-intercepts. So if it's of degree 2, it'll have at most 2 x-intercepts. Think about a quadratic equation opening up where you could have 2 x-intercepts, but you could also have 1 or none. We're going to explore this idea of zeros more thoroughly in the next section. So for now, we're just going to, in example 6, just state the maximum number of real zeros for the given polynomial. Real simple. All you have to do is look at n, which would be the highest exponent, and here n is equal to 112. So 112 would be the maximum number of real zeros for the given polynomial. Easy peasy. So let's just sort of round out this section by looking at some polynomials and matching each polynomial to its graph. So the easiest way to match a polynomial to its graph is to first look at the end behavior. And if that doesn't give you enough information, then kind of look to see how many zeros there are. Okay. I'm going to look at p of x equal to 4x to the 6 minus 3x squared plus 5x minus 2. First thing I notice is that the degree is even, right? So it has a 6, and the leading coefficient is positive. So I have even, positive. So even means both ends, the end behavior, either both go up, both go down. So it could be graph C or graph B. But since the leading coefficient is positive, that means both ends go up. And that would give me C. Okay, so the one underneath, p of x equal to negative x to the 4th plus 1. Again, even, degree, negative leading coefficient. So both ends down. That tells me it has to be B, since the remaining graphs end behavior would be an odd degree. And then p of x equal to negative 2x to the 3rd plus 5x squared. Here we have a odd negative. Odd negative would be either A or D would be odd. So the negative should be D, because that's going to go positive infinity, negative infinity. And then our last would be p of x equal to 6x to the third plus 1. This one has odd, positive, and that would be our remaining graph A, which would go negative infinity, positive infinity. Just looking here at the end behavior. So in this section, there are a few exercises that may ask you to use a graphing utility like a graphing calculator, or you could use Desmos to first graph the polynomial and then kind of talk about the end behavior and so on. I didn't do any examples there. I thought it'd be more efficient for me to just give you the graph and we'll talk about its properties. So that's it for this section here.